Today we will be talking about resource considerations in projects. In fact, we have already dealt with cost, which is a major resource, and we have talked about time cost trade-offs, which is one of the most commonly used methods of dealing with resources as far as costs are concerned. But today we will generalize our discussion to talk about resources in general, and we will talk about resources like manpower, machines and various other capital equipment which are necessary in the implementation of a project. And we will see what kinds of special considerations are required to plan for various types of resources in a project. The first thing that we have to talk about really is talking about the construction of the resource profiles, which means that you would recall that we can start with a project network, and if we impose on the project network the activity times, it is very convenient to determine a project schedule by doing a simple forward pass and a backward pass, which can identify the early start and the late start schedules. This schedule, when depicted as a Gantt chart, would appear something like this. That means for each activity in the project, we can identify the time that that particular activity is going to be taking place. So we can in fact establish this kind of schedule. Now it's quite likely that these individual activities, apart from cost, might require other resources for their implementation. Typically these activities might require, for instance, manpower. They might require some special type of machines. They might require some special equipment. So if we want to now find out the manner in which we are going to be using that equipment, we will have to refer to this basic schedule. So what we can do is, for instance, from the basic schedule of activities, here we superimpose on this the activity resource data. So these figures here shown adjacent to each activity are not their durations. The durations of course are the length of these individual lines themselves, but these are, let us say, the manpower needed for accomplishing each of these activities. It may so happen that activity A1 requires 4 men, activity A2 requires 5 men, and so on. So we have this list of activity resource data which we now impose on the schedule. So if we do this, you can see from this particular example that during the period from 0 to here, 4 plus 2, 6 men are going to be needed. 7 men are going to be needed during this particular interval. Only 5 men are needed in this interval, and 3 people are going to be required in the entire interval from here to the project finish. So depending upon which activities are active at what particular point of time, what we can do is we can determine the resource usage profile. For this particular example, the construction of the resource usage profile, as we have seen, shows that we require 6 men in this particular interval, and then 7 men here, and then 5 men here, and then 3 men for the subsequent part of the activity. So this particular graph is called a resource usage profile. It shows the variation in the resources which is going to be needed to accomplish the schedule which we had required. So what we are trying to say here is that we are going to need 6 people in the beginning till this point in time, and then subsequently we are going to need 7 people up to here, and then there is a drop and we are going to need only 5 people during this particular period of time, and then again there is a drop, and so on. This information is vital to the planner, to the project manager, because it would help him to identify exactly what is going to be the resource requirement for the particular project. And moreover, if you are interested in hiring and firing manpower, it knows exactly, from this information, you know exactly how much manpower is required during what particular periods of time. So you have to make your provisions for hiring and firing appropriately. Similarly, if this is a capital equipment like cranes, you know when to hire how many, and so this particular information again is really very vital when you are trying to talk about the resource profiles. So when we are talking about resource considerations in projects, which is the theme of this lecture today, we are primarily concerned with the construction and the manipulation of these resource usage profiles. Now, before we go into the various kinds of procedures which are available for dealing with these resource profiles, it's worthwhile to make a distinction between renewable and non-renewable resources. And based on that, we would see how the methods available for dealing with these could vary. For instance, let's look at the concept of what we call non-renewable resources first. By non-renewable resources or consumable resources, non-renewable resources are those resources which are often referred to as consumable resources as well. If you look at the resource usage profile of a non-renewable resource, in this category we are basically concerned with the total resource consumption, which means if we are at time t here, what we are interested in is the total consumption, that is the area under the curve up to time t, really speaking. So as when the project ends at the final project duration, the total area would give us in fact the total consumption of the resource. For instance, if you talk about money, right, this is the rate of spending, and then maybe at the end of it you would know what is the total amount of money which has been spent, and we are actually interested in minimizing that particular total sum of money. So here our concern is primarily with the total area or the total consumption. So consumption is nothing but the area under the resource usage profile. On the other hand, if we look at non-renewable resources, here the concern is with the total resource usage at each point of time. That means we are worried about what is the total consumption at this total resource usage here, not the total consumption which has taken place here. Resource consumption is the integral of the resource usage in that sense. But here we are concerned with, for instance, we could be concerned with what is the peak, or what is the minimum resource consumption, or how many dips and how many crests there are in the resource usage profile, and things of this nature. So if you look at the methods available for handling these different kinds of resources, for the non-renewable resource category, typical examples of which are money. Money is a non-renewable resource. I mean, it's non-renewable in the sense that if I have a 100 rupee note today and if I spend it, that 100 rupee note is not available to me tomorrow. I have to have a new 100 rupee note to basically, so in that sense it is consumable. On the other hand, manpower is a renewable resource. If I have one person working with me today, I use him today, I can use him again tomorrow. So in that sense it's a renewable resource. It doesn't get consumed, right? But if you, it all depends upon how you define it. For instance, if you define your resource as man days, that becomes a consumable resource. But availability of manpower is a renewable resource in that sense of the term. So looking at examples here, money, energy, fuel, raw materials are all instances of non-renewable resources. And in fact, these resources are best handled by time cost trade-offs. That means the objective here is to minimize the total consumption of non-renewable resources over the feasible range of project durations. That means whenever we are dealing with consumable resources or non-renewable resources, those which get consumed, which is like cost, we resort to procedures like time cost trade-offs, which are used for basically trying to find out the minimum cost schedule, or trying to find out the best trade-off between the project duration and the project time, this kind of thing. And we are already familiar with these procedures. However, when we talk about renewable resources in projects, and that is our major concern in this lecture, we are actually talking about resources like, as I said, manpower or power or machines or fuel flow. All these resources are basically handled through three different mechanisms. The simplest way of handling these resources is through what we call resource aggregation. You see, aggregation simply means, as the name suggests, is the process of working out the resource usage profile from the schedule. Recall the example that we just did. We had the schedule for a project. If you superimpose on that schedule the resource requirements for individual activities, then you would have the aggregation of resources and you would be able to work out the resource usage profile. That process is called resource aggregation. So resource aggregation is actually simply trying to find out what are the resource requirements for a particular schedule. It does not in any way try to influence those resource requirements. Right? So it's simply like taking a snapshot of a particular schedule. On the other hand, resource leveling is more detailed in the sense that it looks at the resource profile, and you might not find the resource profile very satisfactory. So it might want to change the schedule to get a better, more acceptable resource profile. So essentially that is the process of resource leveling, and limited resource allocation is the process of trying to conform to resource availabilities and trying to minimize the project duration. Is that? So this is, let's look at these things in a little greater detail. So when we talk about resource aggregation, as we indicated, the objective is to construct the resource usage profiles from the project schedule and the activity resource data. These are the two major inputs that you need for constructing the aggregated resource profile. So the result of this would be that you would have the manner in which the resource requirements vary for that particular schedule. This would be a valuable input to the project manager, obviously, for planning both the procurement and the deployment of his resources. Now suppose once we have the aggregated profile, suppose that our original profile is the one which is shown here in this dotted line. We might find that this is a high during this particular period, and we are not really very satisfied with this high. So what we might want to do is we might want to smoothen the resource usage profiles. How can we do that? We can do that by shifting slack jobs without worsening the project duration. That is, the project duration here is fixed, and therefore during this particular period when we have the peak, we can examine which are the jobs which are currently active from the schedule, and those jobs which have slacks, those could be shifted either this way or this way, and this might mean that some jobs are shifted here. So this particular revised profile that we obtain from the original resource usage profile by shifting certain slack jobs is now something like this. It's more level. It has better characteristics than the original profile, and this is how we obtain it. Notice that in this process we have not allowed the project duration to increase at all. Okay. So there are procedures available for resource leveling. there are both analytical procedures as well as heuristic procedures. But the difficulty with the analytical procedures is that they are capable of handling only a small number of jobs or very small projects, and for real life projects it is not possible to do resource leveling for a large project which involves hundreds of activities. For this reason, generally resort is made to heuristic procedures. So although heuristic procedures do not guarantee optimal solutions, but nevertheless they are practical procedures which can be used for this particular situation. During the course of today's lecture, we will look at two of the heuristic procedures which are commonly used for resource leveling. Now, talking about the third problem in resources, that is the problem of limited resource allocation, or the resource allocation problem as it is commonly called. You see, what may happen is that this was our original profile of resources. We went through a leveling process and we found that this was the leveled profile, this dotted line here after this, which was done in project duration T. But what may happen is that our resource might be limited to RL, which is this particular line here. So even the best leveled resource, which was having a peak somewhere during this period, could not be implemented because during this particular period from here to here, the resource requirements were exceeding the resource availability. So if our resource availability is so much, what do we do if we want to implement this particular schedule? Obviously, in a situation like this, what we would have to do is, we would have to delay some of the activities which are going on during this particular time period, right? And once we delay some of those activities, in fact, some of these activities would be critical activities and we might be forced to delay those critical activities, which means that the project duration will tend to increase from T to Ti. That's significant. So what we try to do is, we try to basically reschedule jobs in such a manner that the resource profile is such that all the peak resource requirements are falling within our limited resource availability. And in this process, we are trying to ensure that the increase in the project duration is in fact a minimum. You can imagine something like this, that when you talk about resource leveling, you are holding this duration here, as it were, with a plunger and trying to push it from the top without allowing the plunger to go to the right. That is what resource leveling is all about. But when even the best level resource does not meet your requirements and the resource peaks are higher than the resource availabilities, you have no option but to press it hard and allow this to increase slightly. So the limited resource allocation problem is to determine that schedule for which the increase in project duration is a minimum. This is the problem in limited resource allocation. Let us see how, for instance, these problems can be handled. For instance, look at a small network which has, this is a small network, a very interesting network because it brings out very dramatically how resource leveling could be done. It's an example that is constructed by Wiest to illustrate the basic notion of resource leveling. So here are the activities. The first number is the resource requirement and the second number is the number of days required for the job, right? The resource requirement or the manpower requirement and the time required for each job. And this is shown for each of the jobs for this particular network in the AOA convention. This is shown here. Now if we take an early start schedule for this network, see the early start schedule for this network is in fact shown in this particular graph. This is a time scaled graph, and what we are finding here is that the critical project duration is 11 days. The critical activities are these 6, 7, 2 and 1. In fact, 6, 7, 2 and 1, these refer to both the resource requirements, and also we can identify the activities by these resource numbers because no two activities have the same resource requirements. So if we take the early start schedule, then what you find here is, if we sum up period by period, that is, we do a resource aggregation exercise, we find that in this first period, job number 4, 6, 3 and 9 are all active. So the total resource requirement is 22. 4 plus 6 is 10 plus 3 13 plus 9 is 22. Similarly, for each period we could find out that in this period, for instance, the total resource requirement is 22. Similarly, in this period the total resource requirement is now 24. So that the peak resource requirement of 24 occurs between the second and the third day for the early start schedule. And if we were to implement this schedule, we would need a total of 24 people to be able to implement this particular early start schedule, right? This early start schedule, when shown on a typical resource usage graph, looks like this. It shows that there is a peak of 22 people during the first 2 days, then a peak of 24 people, and then it drops down, and then you have the resource fluctuations. There's only one man needed from the days from 7 to 11 as far as this particular project is concerned. So it's a highly imbalanced kind of a profile, because otherwise also in an early start schedule you expect that most of the resources are going to be consumed early, and during the later half you are not using many of the resources. So this is what is typical. For this particular example, if we look at the test leveled schedule, notice what we have done. The critical path remains the same. The activities here are 6, 7, 2 and 1. The best level schedule will have to be worked out by some heuristic or by some procedure maybe. But in this case you see that the activity 9, which was earlier being done at the earliest, is now being shifted to the latest position. This activity continues to be done at the earliest position, whereas these two activities 3 and 8 have been shifted so that they are done at their latest positions. So it is some combination, and what you find as a consequence is that the number of men required for on each day is 10, 10, 10, 10, 10, 10 throughout. Now this is obviously, in any practical resource leveling exercise you may not be as fortunate as this, because this, as I told you, is a specially constructed example by Wiest which shows this. So the best leveled resource profile in this case, corresponding to this schedule, it's a perfectly leveled resource profile, and 10 men are required throughout the time duration of 11 days for this particular project. So this essentially is the concept of resource leveling, whereas corresponding to the early start schedule we were requiring a total of 24 men to implement the job. Here the same duration can be achieved with only 10 men if we have properly leveled our resource requirements, and it's a much better schedule because all these people are not are being utilized uniformly throughout the project. But if you follow the other case, you would have lots of costs of hiring and firing people, and you might even have difficulties in trying to recruit manpower for doing that kind of job. especially if the resources that you are talking about are skilled resources, like skilled engineering manpower or skilled managerial manpower, then their availability is typically limited and it becomes very difficult to find or implement a schedule which has a lot of fluctuation in the resource profile. Now, from this example, we will today look at some procedures for resource leveling and defer the discussion on resource allocation to the next lecture. So, let's look at typically some of the major criteria which are involved in the resource leveling process. So, let's look at the criteria in leveling. Different authors have suggested different criteria to be used for resource leveling. One of the most commonly used criteria is the peak level of the resource usage. The peak level of the resource usage means you look at the resource usage profile, and wherever is the maximum resource usage, you try to minimize that, and that is the objective, they say. In fact, there is a trigger level setting heuristic of WEAST, which we will discuss shortly, that tries to look at this particular criterion and bases its entire computation with the objective of minimizing the peak. However, what is the major defect with this criterion of the peak? The major defect is really that when you have the entire resource profile, you are looking at only the worst part of it, one particular area where it is worst. And rather than trying to develop an objective function for the entire resource profile, see, what can happen is that there might be just one resource, one peak, and the other resource profile might be acceptable to us. So just for the sake of one peak, it might not be worthwhile to penalize that particular resource profile unnecessarily. So it has been suggested that maybe a criterion like this, the sum of the squares of the resource usages, could be a very good criterion to find out how good the resource profile is. Because obviously, for all schedules, the total area under the resource usage curve is a constant. It's like when work is scheduled, the total work done has to be the same. But if there are imbalances, it's those imbalances that we are trying to talk about, and the sum of the squares of the resource usages, if we try to minimize this would be a good idea. Maybe to give you some intuitive concept of this particular resource, for instance, suppose that we have a resource usage for 2 days, which is, let's say, of the order of 4 men are consumed on the first day and 4 are consumed on the next day, right? This is the best possible thing which can happen. It's perfectly balanced, right? Let's try to increase the amount of imbalance in this. What can happen is 3 men here, 5 men here, 2 men here, 6 men here, 1 man here, 7 men here, and in the worst case you have 0 men here and 8 men here. It could be distributed either this way or that way, it doesn't really matter. So what you really see is that if you look at the sum of the squares, in this case you will have 16 plus 16, here you will have 9 plus 25, here you will have 4 plus 36, here you will have 1 plus 49, here you will have 0 plus 64. So you find really that the sum of squares is minimum and is equal to 32 when this is best balanced, which is 4, 4, and it is worst, it is equal to 64 when it is the worst situation, when there is no man operating here and all the 8 people are here. And in between you find that from 64 to 50 to 40, 40 here, 50 here, 34 here. So there is a progressive decrease. So this is the intuitive concept behind using the sum of the squares as a criterion to measure the effectiveness. So if you have a large resource usage profile, you have a profile, for instance, which reads something like this. You have all kinds of fluctuations in this. What you can do is you can find out the resource usage on the first day, square, on the second day, square, and so on. If this runs up to n capital days, so this entire thing would give us a measure of the degree of balance of this particular profile. Incidentally, this is the criterion which has been used by Burgess and Kilbrew in using their particular algorithm. So broadly speaking, let's see the logic of the workload smoothing heuristic due to Levy, Thompson and Wiest, which was proposed very early and which has been patronized by Wiest. The basic procedure can be described very simply. You start from an early start schedule, as we do earlier. And when you start from an early start schedule, corresponding to this schedule, you can work out the resource usage profile, just as we did. Once you have worked out the resource usage profile, you can know where the peak resource level is. And this particular heuristic identifies that peak and it starts to set a trigger level. That's what it does. It sets a trigger level 1 unit below the peak. That's what it does. So this is the basic idea in the whole procedure. A trigger level is actually a kind of a target, you can say. You are trying to reduce the peak of the resource usage profile by 1 unit at a time. And since you already have a peak which is a certain value, your target is now 1 unit below the peak. And then what you do is you examine the jobs which are currently going on during that particular peak period, during the peak period. And what you try to do is you try to shift those jobs to find a schedule that satisfies the trigger level. So if you find that there are a number of jobs who have enough floats so that they can be shifted beyond the peak, then those jobs could become candidates for shifting, and you could reduce the duration of the peak, hopefully, right? So this is the general logic. So you shifting jobs to find a schedule that satisfies the trigger level. If you cannot find, if this is not possible, if there is no schedule possible which satisfies this new trigger level, you would stop. That means the one particular schedule that you have is already the best schedule. Otherwise, you continue, and continue means you found a better one here. So you set your new trigger level 1 unit below and continue the process in this particular manner. One feature which has been introduced into this particular heuristic is the element of randomness. Randomness essentially means that you have to examine jobs which are going on during that particular peak period. So suppose there are k jobs going on, you call them A1, A2 and so on up to AK. You have the option of shifting any one job or a combination of jobs so that the peak is reduced. So which job you pick up, it can be done by a random process out of the available candidates. The advantage of randomness would be that when you run the program the next time, you can have a different solution. So if you run it maybe 20 times, you will have 20 solutions and you can pick up the one which is the best. That is the basic advantage of this particular heuristic. Let us now look at the other heuristic.
So in this heuristic, when we run the program again, is it possible that we get another solution? Means the first time the peak reduces by 10 minutes. Suppose we run it at a time, then it reduces to 12 or 13 minutes.
That's right, it can happen. Because because of this element of randomness, what can happen is that the first time you run the program, you are able to reduce the peak from maybe 20 to 18. But the second time you run the program, you might be able to reduce it from 20 to 17 more, or even less, as the case may be, because there is no guarantee of optimality in the entire procedure. What we are simply doing is examining the jobs which are going on during the peak period and making a list of those jobs which could be shifted. And in making that list, we are making sure of two things: those jobs which have enough slack available with them so that they can be shifted beyond the peak. Those are the jobs which should really be shifted. But it's not necessarily true that shifting those jobs will necessarily give you a schedule, because what can happen is shifting one job from here to there could create a new peak somewhere else. And the advantage of the trigger level is that we don't want to exceed the trigger level at that particular point. So all schedules which give you peaks above the trigger level are actually ignored, and only if you find a solution which gets you a schedule below the trigger level, you store that solution. That's the basic idea. So this is a heuristic in which the objective function is to minimize the resource peak. The second heuristic that I'll briefly discuss with you is the Burgess and Killebrew heuristic, which is actually an 8-step procedure designed to minimize the total sum of squares of the resource usage. So the objective function is to minimize the total sum of squares of the resource usage. And I already gave you an intuitive understanding of this particular objective. So it thus looks at the whole profile and not just the peaks, this particular procedure. And in case of multiple resources, the most important resource is considered first, followed by the next, and so on. For instance, you have two resources like skilled manpower and cranes. If you think skilled manpower is more important, then apply the heuristic with first the skilled manpower, and then keeping that as constant, try to work up the cranes. So I'll briefly go through the steps of this particular procedure so that you have an idea. The starting step, or the initialization step, simply looks at basically listing project activities in order of precedence. In fact, as you know, any topological ordering of the activities of a network is will give you the activities in order of precedence, and therefore this ordering is not unique. So in order to pick up a specific ordering, what these people have done in this particular heuristic is that they say that you arrange the activities in order of precedence by arranging the arrowhead numbers in ascending order. So each activity will have ij. J is the arrowhead number. So you arrange the activities in arrowhead number, and when two or more activities have the same head number, that means when there are a number of activities culminating into the same node, then list them so that the arrow tail numbers are also in ascending order. So basically, by following this numbering scheme, you have in fact a unique listing of the jobs for a given node numbering scheme. Of course, if you change the node numbering scheme, you will have a different order, right? So then you add to this list the following information: the duration of the job, the early start, and the slack values. What is the total float for each activity? That's the information that you would require. What is then done is, you have a list of the activities in the order of precedence. In this list, you start from the bottom. So what it says is, look up the last job first, starting with the last activity, the one at the bottom of the diagram. Schedule it to give the lowest total sum of squares of resource requirements for each activity, each unit. You look up the last activity. The last activity can be slided this way or that way depending upon its float. So we pick up a position for that activity in that slot where the total sum of squares of the resource requirements is minimized, and then we fix that activity there. Another important thing is that if more than one schedule gives the same total sum of squares, then schedule the activity as late as possible to get as much slack as possible in all preceding activities. So that's the logic. So essentially speaking, it is just a process of shifting each activity. When we shift the activity, we can keep it either at the earliest value, or we can shift it by 1 day, or we can shift it by 2 days, or at most we can shift it by the amount of total float for that activity. So you compute for each of these what is the total sum of squares of the resource usage, and wherever it is minimum, freeze the activity there. And if there are possibilities that either here or a later value gives you the same sum of squares, keep that activity as late as possible, so that the earlier activities can then have more of float, right? Step 3 then says that the last activity which we have just considered, keep it fixed and repeat the earlier step, step 2, on the next to the last activity in the network, taking advantage of any slack that may have been made available to it by the rescheduling in step 2. So once you have taken the previous activity and have fixed it, the other activity can now be slided up to that point. So find out now for the next activity as to where it can go, and again try to fix it so that the sum of the squares is minimized for that particular activity. That's the basic logic. And basically we continue this step. So step 4 of the algorithm says that continue step 3 until the first activity in the list has been considered. This completes the first rescheduling cycle. So this is basically one complete iteration of the algorithm. So what you do is you start with the early start schedule, you have a Gantt chart of the activities, start from the lowermost activity, shift it depending upon its float, and freeze it where the total sum of squares is minimum. Then take the next one and again do the same thing, and the next one do the same thing, and the next one do the same thing, till you come to the top of the list, which is the first activity, and then this completes one rescheduling cycle.
So each time the sum of square changes.
That's right. Each time you shift an activity, the sum of the squares of the resource usage will change, because each activity is consuming some resource.
Yes.
So shifting it would mean that its position changes, so the resource usage and the resource requirements will keep on changing. Not only this, in fact, with additional rescheduling cycles also, the sum of the squares could change. Why? Because we are taking one activity at a time. We have fixed up this activity and then we change this activity. It's quite likely that when we do this again, there could be a further change in sum of squares because of the changes that have now been made globally, right? We are handling one activity at a time essentially for ease of manipulation.
Sir, is it necessary that we must shift complete activity? Can we break up activities?
No, we take up each activity and we shift the activity as a block. The activity is shifted depending upon its total float by 1 day or 2 days or 3 days. What you are probably referring to is the process of splitting the activity.
Yes, sir.
If there is a possibility of splitting the activity, then you can use the same algorithm. What you can do is the original activity can now be modeled as 2 activities in series, and each one of them can now retain their structure. So then they would have the flexibility of being split. So this is possible using the same algorithm. The next step in this particular algorithm would be to carry out additional rescheduling cycle. That means from normally most of the changes take place in the first rescheduling cycle. Second rescheduling cycle, very few changes take place, and typically in the third rescheduling cycle there are no changes. This is what is the normal thing. So carry out additional rescheduling cycles by repeating steps 2 through 4 until no further reduction in the total sum of squares of the resource requirements is possible, noting that only movement of an activity to the right, that is scheduled later, is permissible under this scheme. You see, since we have started with an early start schedule, you are only investigating the possibility of shifting the activities to the right and not to the back to the left. So it's a one directional search. And you might have shifted it by 2 days, the total float is 4 days. So in the subsequent rescheduling cycle, you will again investigate the possibility of shifting the activity only by 2 additional days and not by the whole amount. So the subsequent rescheduling cycles would in fact reduce the amount of shift that is possible for each activity, right? So you continue this for the things till there is no further reduction in the sum of squares of the whole activity.
So how to find out that now no reduction is possible?
No, you know the first rescheduling cycle, you calculate the sum of the squares at the second rescheduling cycle. If it is lower, then you go for the next one. If you find it is the same as the previous one, then you know, then you would stop. So if this resource is particularly critical, then repeat the whole process, he says, on a different ordering of the activities, which must, of course, must list the activities in order of precedence. Okay? We started off with one particular precedence order. You know that there are many topological orderings. You can start with some other topological ordering and do the same thing. And since it's a heuristic procedure, you might get a better solution. That's the only thing. He says if this resource is critical, then you might as well do it for a couple of different topological orderings, and there is a possibility that you might get.
So in previous we selecting the last activity. Now we can select middle one or anyone.
No. The starting procedure would be the same. The last activity you would take and go through this from the last to the first. But the sequence of placement of activities is topological order. Yes. So the last activity might not be the last one. It might be the last but one activity. I mean, if there are 3 last activities in a project which have no successors, then there could be 3. They could be in 3 different sequences. So that possibility can arise, right?
Yes.
Step 7 of this particular procedure specifies the choose the best schedule of those obtained in steps 5 and 6, right? That is when you tried this. And the final step says that having obtained a schedule, you can make some minor adjustments to it manually. Make final adjustments to the schedule chosen in step 7, taking into account factors not considered in the basic scheduling procedure. So that means if there are any practical constraints which you want to incorporate, those could be incorporated in the schedule and manually modify it before you take. Just to give you an example of how this particular schedule works, here is a small network which has 9 nodes as shown here. Nodes are numbered from 0, 1, 2, 3, 4, 5, 6, 7 and 8 as shown here. The number here shows you the duration of the activity, and these 2 numbers show you that there are 2 resources. This one is manpower and this one is the number of cranes, let's say, right? Number of material handling equipment needed for this particular activity. So some activities require no men here but some cranes. Some require 3 skilled men and no cranes. So this is manpower. There could be some activities which require both. So we are talking of 2 types of resources. So if you carry out a forward pass in this particular network with these time durations, you get these earliest occurrence times. If you carry out a backward pass, you have these times which are shown in these triangles here. These are the latest occurrence times for the nodes, and you can easily see that this is the critical path for this particular network. That means it has a duration of 15 days, and these are the resource requirements for this particular activity. Now for this particular network, the Burgess-Kilbrew procedure, which you just applied, was applied, and I'll just show you the final results in terms of what was observed. Really speaking, what happened was that before and after, we started with an initial early start schedule. The initial resource profile for resource A was something like this. So you find this is for 15 days like this. These are the resource requirements on 15 days. The peak was occurring on the second day and the peak was 14. Whereas the final resource A profile after this procedure was something like this. So that the peak now was only 9 days and it was occurring on these 3 days here. So there was a substantial reduction in both the peak and the total sum of squares for this particular. Similarly, for the resource B, the initial resource B profile was something like this for that network. The resource peak was 8 days, occurring on these 4 days. After the solution was applied, the peak resource day was still 8, but of course the duration had gone down from 4 days to just one particular day, and this was the consumption of resources as far as final resource B was concerned. And for this network,
so first you use this method for resource A and after it resource B.
You do it for both, yes, but you take it for resource A, right? First you use it for resource A because resource A was important, and after having done that, you can do it for resource B.
So for doing resource B, it may change the position of resource A.
You will not make those changes which result in worsening of the resource profile of A, right? In this particular example, the initial sum of squares for resource A was 738. It was brought down to 626, and for resource B it was brought down from 416 to 375. So this was the final result for this particular problem. So this gives you an idea of how these two heuristics, namely the trigger level setting heuristic of Wiest, which is primarily aimed at bringing down the peak, and the Burgess and Kilbrew heuristic, which is looking at the entire resource usage profile, can be used in practice. In order to summarize what we have tried to do today, we have seen that we have discussed the notion of renewable and non-renewable resources essentially in this particular lecture. We have seen that time cost trade-offs are a legitimate means to handle non-renewable resources like costs and things like that. Renewable resources like manpower and capital equipment can be handled by one of 3 possible approaches, which we have seen. These 3 approaches are the approach of resource aggregation, which is merely taking a snapshot and trying to find out what are the requirements of manpower for a given schedule. Then, if you are not satisfied with that profile, you can resort to leveling and bring down the hiring and firing costs and have a more balanced leveled profile. And the third technique for dealing with these renewable resources is limited resource allocation. Heuristic procedures for leveling were presented. We looked at 2 such procedures, and a sample problem was solved using the Burgess and Kilbrew heuristic. Thank you.